Welcome to Mojo community meeting. We'll wait a minute or two for more people to join, but we have a very exciting program today. We start from Chris Lattner talking about Macs and Mojo and GPUs. And then Brian will talk about his thoughts on Async. And then we will finish with Q&A as usual. So let's see. Let's wait maybe 2 minutes. And then Chris, it's all yours.
All right, just let me know.
Okay. Just giving people a few minutes to join.
Yeah, no problem. Let's see. Does this look okay?
Yeah. Okay, let's start.
Cool. Well, welcome everyone. We're excited to give a quick update on GPU stuff. We've been working on this for quite some time. We're trying to do something really meaningful. Just for context, this is kind of an extended, hacked up version of a talk I gave before, and so I'll kind of skip through some pieces pretty quickly, but hopefully it's interesting and gives you some context. All this stuff is coming together soon, so we're working really hard on this. It's not quite available today. We'll talk more about concrete time frame at the end. So first of all, let's talk about why we're doing this, right? So I'll give you kind of my personal journey. I've been working on compilers and languages and stuff like this for a long time, as many of you know. And what really started happening is that architecture started changing. Accelerators started happening, GPUs, other kinds of ASICs and things like this. I was fortunate to be working with Dave Patterson, and when he got the Turing Award, he gave this amazing talk about for people designing hardware, it's this amazing time because you get to design all these new things and people suddenly care. And so my experience at the time was working on things at Google. And so I was, again, fortunate to be in this playground of all this new technology where we were building TensorFlow back when it was cool. and what I saw is that like every new technology got a new piece of software for it. And so TensorFlow had its graphs, NVIDIA had CUDA, of course. TPUs built this XLA compiler thingy. Android and mobile things had TensorFlow Lite. Google had tons of other chips going on at the same time, and each of them had weird different software stacks for this. And so one of the things that came out of this was we realized we needed a unifying theory. And so Tatiana and I and several other people said, let's build a new compiler stack. And this is where MLR originally came from. Later, I left Google for a variety of reasons and joined a little hardware startup called Sci5, and we were trying to build an innovative new RISC-V based AI thing. And so it was very, very, very exciting, all kinds of cool technology, building the hardware, following exactly what Dave was saying, but then realized that there's actually no AI software. So again, smashed directly into this problem of, we need actually a software stack for accelerators, and we need something that's reusable. And so being the smart guy that I am, what did I do about this at the time? Well, I just complained to academics and talked about how terrible the whole world is. And so I wrote this talk. You can find it online. There's a YouTube video saying, look, it's not just the golden age of hardware, it's the golden age of compilers and system software as well, and saying somebody needs to go build a unifying theory for somebody to plug into. And of course, this didn't work. Why didn't this work? Well, this is, even individual megacorps trying to solve for one chip can't solve this problem. But also, when they do, a megacorp that's trying to bring up a chip just wants to solve for their chip. And when they do that, they want to lock you into it. And it's not necessarily malicious, but it's kind of natural that if you're building an entire software stack for one chip, then you're not going to worry about other people's stuff. You have big enough problems. Finally, second is that within the MLIR community, for example, there's a lot of fragmentation, infighting. A lot of the dialects and the trees are a mess. They don't really work. And it's a huge, huge industry problem here. And finally, it's just ridiculously expensive to build this stuff. You need a huge team of specialists. You need good leadership. You need a lot of other things to go into it. And so this is the origin story of why Modular came to be. Right? And so we weren't here to just build a better Python, obviously. We're here to actually lift the state of the art of this entire category of hardware and accelerators. And so what we decided to do is take a very methodical approach to how we tackled this and actually build the components in a way that we couldn't do that when at a big company, you care about a 6-month or 1-year performance review cycle kind of a thing. And so we laid out a bunch of really big goals. And so this will help explain how we work if you understand our goals. we wanted to beat the state-of-the-art performance on existing chips, things like Intel chips or NVIDIA chips, beating the vendor's performance on their own hardware. That's a big goal, right? They're the experts in their own silicon. We want usability. So you know what Mojo is, obviously. We want to be able to drive the state-of-the-art in usability forward. This is a huge deal that, for example, hardware makers typically don't care about. They just care about it being possible, not about it feeling great. We want quality. We want to upgrade things like PyTorch and other AI stacks to actually work well and actually be designed as a production quality kind of infrastructure. We want new research. We want new generality. We want people to be able to innovate at all levels of the stack. And so one of the things we did about a year ago is we launched our CPU stack. And so within this, you look at, well, why is that hard? Well, within this, you have lots of different macro architectures. So things like x86 or ARM64. You have tons of microarchitectures within them. And if you're writing a web browser or something, each of these microarchitectures doesn't really matter much for performance. But if you're writing a matrix multiplication, you know exactly the size of the cache hierarchy. You need to know exactly the new dot product instructions. You need to use all the crazy features that people are adding. And you need to be able to scale across the massive complexity that this hardware landscape provides. And of course, logicians know that there's things like SIMD and threads and things like this. And the programming model for all this stuff is nascent, even for, like, again, C++ developers who've been working on this stuff for decades, right? And so this is actually a really, really, really hard problem. And so when we walked into this problem, knowing how hard it is, we decided to take the, perhaps slower, but the path that would lead to the better outcome. And so we decided to take a new approach. And so, again, this talk was kind of adapted for other folks. I'm not going to tell you what Mojo is. I assume that if you're here, you kind of know that. And so systems programming language, it pulls together the best part of Python and PL and compiler design. And so the cool thing about this, and the thing that I think is really important about this, is that, as you know, Mojo is not Python, but it pulls together the Python developers and also the ecosystem of packages in a way that allows us to, like, really spring into this opportunity without ignoring the past. And to me, one of the key things about what Mojo is doing is it's trying to give superpowers to programmers who probably wouldn't program a GPU before. And so I think that accessibility aspect is really, really, really important. This is a slide. I think hopefully you know that Mojo is fast, right? But the point here is that if you're a Python programmer, there's just things you would never do in Python because it's too slow. Like, you'd never write for loops with math in them because that's too slow. And Mojo makes it super accessible. Now, the consequences of this, again, you pull this all together. We're trying to do this. We've been showing lots of different performance things over time. Llama.cbp is kind of state of the art for Llama 3 inference on CPUs, for example, and they have new innovative things like Int4 and Int6 and Int6K and, like, all this kind of stuff. And we have some really cool results that show that we're significantly beating them on time to first token for Llama, using Mojo, using Max, using this whole technology stack that we're building out, which is really cool. But anyways, we're here to talk about GPUs. So I want to talk about, with that as context, what do we mean by GPU? What are our goals? What does success look like? Because I think that's a really important part of understanding how we're approaching this and what it means. And so let's start with the use cases. Well, the basic use cases are, we want to be able to write a GPU kernel. So we want to write a pile of Mojo code, have a GPU kernel, export PTX, and then you can take that PTX and put it in some other system that already exists, right? Why is this? Well, there's lots of people using GPUs for lots of different things. We'd love to raise the state of the art, but our entire approach is about meeting people where they are, enable them to use bits and pieces a la carte of the tech. And if you want to use Mojo to just write a GPU kernel, that's awesome. Another thing that's really important is that the AI community is very, very connected to PyTorch, and that's a very important technology for lots of different reasons. And so we want to be able to extend PyTorch with kernels written in Mojo. Now, there's other ways to do this, like Tritonling and other things like this. I'm not going to talk much about all this kind of stuff, but we think we can be way better and address some of those challenges, but also have other performance benefits as well. I'm not going to talk very much about PyTorch in this talk, but perhaps if you're interested, you can come to the PyTorch conference. We'll be giving a talk there, and we can talk about it there. But finally, we want to move Gen AI and LLMs and like this entire category forward. And so if you zoom into what is Gen AI, there's lots of different things, including a lot of nonsense. But from a tech perspective, they're super complicated. And if you look at this, you look at what LLMs and GPUs connect at, it's not just about a kernel. State-of-the-art performance requires, yes, you have really fancy kernels, and there's lots of complexity within the GPU. Like on Hopper, there's TMAs and asynchrony and like all this kind of stuff. But a lot of the performance that comes from AI LLMs is no longer the graph or no longer the kernel. It's all about how you orchestrate. It's about how you do page attention, how you optimize your KV cache, how you use mixtures of experts. And so now you need a fast orchestration language, and you need a scalable subsystem that goes beyond this traditional AI graph. And also, one of the things I love about the AI industry is that there's so much research happening. It's super well funded, obviously, but because of that, the research continues really quickly. And so what the world in general needs is this full stack ability to hack and change and evolve this very complicated stack that is also quite a mess. And so for us, if you go back to use cases, given this as context, we want to make it so you can write Mojo and Max native inference models. And we're focused on inference now. We'll get to training later when time permits. And so we want you to go invent a new attention mechanism and put it into an existing model like Llama 3. We want you to have direct control over batching and queuing and like all these different things. We want you to be able to directly manipulate a KV cache. Like those, we want you to be able to build the stuff into a product. That's something a lot of people don't even think about. And so like that now means we need to provide like a full stack solution here. We also want this research piece to be just significantly catalyzed. And that's one of the things I love about LLVM or MLIR or other things we've done historically, where it enabled people to do new things that we weren't even imagining. And so if you haven't seen it, Talife has this really cool India project where he's saying like, I will just go build a training framework and like go nuts. And I love this. And this is one of the reasons why I love communities. And he's not saying like, I need Modular to go do something for me. He's saying like, I will just do this and go and make this happen. And so I love it. This is awesome. And this is the sign of the kinds of things we'd love to see. And so when you look at, again, these goals, you say, well, what do we need to do? Well, we need to solve or at least address the full problem. And so when you look at this, when you think about a GPU, it's not just about the kernel. What you need is host device communication. You need the orchestration logic on the CPU to be able to talk to the stuff on the GPU. You need multiple GPUs. It's actually super common, particularly in fine tuning or large models, to have multiple GPUs, particularly when you get to training, things get much more complicated. We want to unlock the full power of the hardware. Mojo, that's really what it's designed for. We want heterogeneity. And so you want your high performance, multi-threaded tokenization stuff happening. You want your post-processing, you want networking, all this stuff, talking to your GPU compute in the middle. We want a programming model where you can write host code and GPU code in the same file and have the compiler and text split them. And finally, we want good tools. And so a lot of this is why when you say like, what is modular building? Well, we're not just taking a programming language and adding a PTX backend. If you want that, you can use Clang or one of the many things that can do this. What we're doing is we're tackling this bigger problem that enables us to write unit tests and actually use the stuff to solve a problem. And so this is what the Max framework is. The way we look at Max is it is an AI framework for Gen AI, but also for integration with PyTorch. And so I'm not going to talk about Max in depth, but what it does is it brings together a lot of the things that we as an industry have been building into things like XLA or Onyx Runtime or TVM or other things like this that mean that you get great performance, great hackability and stuff like this, and you don't have to micromanage this thing. So let's talk about now getting into the code. How does this come together? Well, so first of all, we think it's really important to, again, meet people where they are. And so in Mojo, it's very extensible language. You can write something that looks literally like a CUDA kernel using threads and blocks and all this normal abstractions that you would see if you're familiar with GPU programming. You get the WMA instructions, and so you get very low level access to the GPU. And it's very important to us that we don't, quote unquote, get in the way. Now, This is brought to you by Mojo and a lot of the tech we've been investing in, because we can talk directly to low-level primitives, and then we can build nice libraries that give you, it's the CUDA programming model, but way nicer. And you don't have C++, you get split compilation, all this different stuff. The other cool thing about this level of abstraction is that you can do ray tracers or other things that have nothing to do with AI. And so we're very focused on solving some of this AI infra problem, but a lot of what we're building is, if you want to build a ray tracer, you want to build something completely different, you can go nuts, and this is all super useful. If you build up, I assume that many of you know Mojo if you're at the Mojo community meeting. One of the most important things about Mojo is we allow library developers to build high quality libraries on top of low level features. And so one of the things that we allow is then you can go build these things. We provide some, you can use them and hack them if you want, but you can also build your own and ignore our stuff if you'd like, and build abstractions. And so, for example, air quote, tile-based programming model to be Tensor Core first is a very popular approach to do this. We're building a library for this that we'll share. And this makes it really easy to use these high-level features in a way where you can, yes, you can use .vectorize and .distribute to actually take advantage of the capabilities of your modern NVIDIA GPU. Now, this is something that, if you're in the space, is actually extremely controversial, because there's been a push towards these air quotes sufficiently smart compilers, things like XLA or things like Triton Lang or things like this, where they're like, trust us, just write code, we'll make it magically fast. But then what ends up happening is it's never actually magically fast, and it ends up being that you have to understand the full stack technology that you're building on top of in order to be able to control the machine. And for a GPU, you need, like, the whole reason you're using a GPU is for performance. And so you want to be able to understand and control this thing. And so this is where the Mojo approach is so valuable. Now, again, Mojo, hopefully, this Mojo has lots of advanced features, including metaprogramming pieces and all these different things. So being able to build, particularly on a GPU, these really advanced pipelines that allow you to be able to control things like asynchronous memory fetches and compute and overlap all this stuff and take full advantage of this is really quite important. And you can do that in libraries. But then also what Max provides around this is it can actually pick up your GPU kernel and do really high-tech compiler things going beyond what we've shown much on CPU. And this includes things like staticization, autofusion into other kernels, memory planning, and things like this. And so this is one where we'll be talking about this more shortly, but this is where the integration between Mojo, MLIR, and then being able to work with the IR that comes out of this is really, really quite profound and enables us to do things that people haven't done before. So if you build, so that's the Mojo writing kernels level of the stack, but the best kernel is the kernel you don't have to write. And so some people really love writing low-level GPU code, and we have a number of those, and lots of other people are working on lots of different kinds of things. But a lot of what the AI world and other people want is they want a higher level abstraction. And so this is something that, if you're familiar with technology like XLA, for example, you can have a very simple graph abstraction, which then allows you to produce a fused kernel. And so Max takes the next step beyond technologies like XLA and provides a state-of-the-art graph compiler. We support full dynamic and parametric shapes, so that you know that you have a batch dimension flowing through your graph, for example. Full extensibility with Mojo, of course. You get automatic kernel fusion. Oh, by the way, all of the kernels in Max are written in Mojo. And so this isn't like a theoretical extension thing. This is like the core way the entire stack is built. And so the cool thing about this is if you're an AI developer, or if you know numerics and you're thinking about things in terms of tensors, you don't have to write a custom kernel. Like, that's actually huge, and that's a really, really big deal, and it's quite profound. Let's go above this. And so the next step up is that you actually have to be able to control your devices, right? And so again, to certain kinds of developers, you just want to say, hey, I'm going to take an AI model and go run it. But other people are much more advanced, and you want to be able to control, for example, I want to go mutate memory on the GPU. I want to go launch individual kernels. I want low-level direct access to this. And of course, This isn't for everybody, but for the people that this is important to, this is really quite important. And so one of the things that Max provides is a full stack driver, kind of analogous to the CUDA driver, but completely independent of it, portable to different hardware. And so what this means is you can allocate and open a GPU, submit kernels, do different work with it, which is all very straightforward. But you can also allocate a CPU and say, hey, I'm running on a CPU. Let's do the same thing with a CPU. And now I have multi-architecture support that now all supports acceleration. And so this is really important because this abstraction of I have a accelerator, I'm talking to it, I'm giving it work, is actually a core thing that, yes, GPUs, it's very important, but it's also about distribution eventually. And so in time, we'll phase in the ability to open up a CPU on another machine and things like this. And so this abstraction is both extremely powerful, hopefully very familiar, but also enables you to get a lot done and control things at a low level. And so we think this is going to be very important for researchers. One thing I'll say about the graphs and the drivers, we love Mojo, and so we have Mojo APIs, but we're also adding Python APIs for people that don't want to use Mojo. And so you can use Mojo to write custom kernels if you'd like, but if you still love Python, you can use Python too. Going up a level. So again, I talked about the sufficiently smart compiler and how it never is. Well, one of the things that's really important is developer tools. And so on GPUs, that's really about the NVIDIA tools. And so they have tools like CUDA GDB, they have profilers and things like this. And one of the major important things for us is that we actually get we have provided and we're building full integration for things like CUDA GDB, the Insight Profiler, integration of VS Code and things like this. And if you've been using Mojo so far, this is something you'd come to expect, but this is also a significant amount of work, and it's really the difference between high quality tools that can scale and also and more research projects. So Darren mentioned on Discord the other day something that's another benefit of all this stuff. And so what we've done is we've replaced effectively the entire CUDA stack all the way down to the bottom level, the low level CUDA driver. And so one of the consequences of that is it gets us out of the CUDA version nightmare because we're not depending on all the different crazy CUDA libraries at all the different levels of the stack. They all have to line up exactly. And so one of the things that's super cool about this is that this CUDA versioning nightmare, I mean, if you're using PyTorch, PyTorch has its own problems, but if you're using the Max native stack, the CUDA versioning is solved. You don't have to deal with this anymore. You still need to install CUDA, but there's nothing to mismatch. And this is, I think, extremely powerful, and I think will hopefully significantly reduce suffering in the world. And so we talk a lot about usability and capability and our goals and things like this. We don't have the full performance results we want to share yet, but one of the things that's actually really cool about this is we've previously told people and said that we're already beating NVIDIA's performance on their own chips. And so we compare against state of the art. We're not comparing against things like PyTorch or XLA or things like this. We're comparing against cuBLAS and Cutlass. Cutlass is one of the fancy C++ libraries that NVIDIA is using for being able to write GPU kernels. And so you can see very competitive performance across the board, but also we're winning by something like 20 to 30% on straight matrix multiplication. And so matrix multiplication being one of the most studied problems and most optimized, if Mojo's beating state-of-the-art matmul by 20, 30%, you can imagine what we're doing on full end-to-end model performance. So, and this is power coming to you soon. So one thing I'll just say and reinforce is that Max isn't about AI. This is also about accelerated compute. There's lots of different applications. I know it drives people crazy that we talk so much about AI and all the stuff that we build is extremely general. The reason for that is just focus. Like we have a small team compared to the scale of the problems that we're tackling. And so this is where, we'll continue to do the AI thing, but we'd love for community members to go push on HPC or data or weather forecasting or like whatever the other things are. And so we just don't have expertise with that. So wrapping up lightning talk, the whole point with our technology is we're trying to give superpowers to developers. We really care about unlocking and catalyzing this next generation of compute. We think there's huge opportunities for the entire world here. We just have to get it so people can use it and make it so there's less suffering in this world. And in doing so, we think that we can get a lot more innovation, a lot more creativity, and a lot more joy out of this whole world. And so what can you get today? Well, today, unfortunately, we're still on CPUs. And so you can get things like Llama 3 if you haven't checked it out. We have builds.modular.com with a bunch of examples. This will get expanded in the next couple of months, but we're trying to make it really easy to build and deploy this stuff. If you're doing traditional AI stuff, Mac supports Onyx and TorchScript. We have PyTorch, Dynamo, and all that stuff all going. Mojo's amazing. Y'all are amazing. And so if you want to follow the cool hotness, please check out the nightlies. One thing that we're excited and we're going to be working on, we'll talk more in a couple of weeks, I think, is Mojo is getting out of the modular installer. And so we're removing the auth requirement. We're providing pip and conda packages. We want to make it so that it's super easy to integrate into all of your applications. We have this new tool called Magic. And so if you'd like to join the alpha, you can go to this modular.com or modular./magic and try it out. This is a super fast, awesome install experience, makes it so you can get up and running really quickly. And so we're continuing to build into this and make it so that you can integrate and use Max and Mojo for all the different kinds of things you want to do. So when is this shipping? So, so good news, bad news. Bad news is it's not today. Good news is coming very, very, very soon. Our approach on this is that we want to work with y'all, the developer community, first. And so our plan is September, hopefully early September, but we'll see exactly when in September this comes. We want to provide it all in the Max Nightlies. And so this will include a bunch of examples and demos and stuff like this. Let me reinforce what we're building here is really hard. And so I expect the initial bits to be pretty rough, but we'll bake that out later into the fall. And then as it gets more baked out, we'll have a full PR launch with fancy video and other collateral and things like this. We've done videos and things before, so we expect it to be similar or better quality to the previous ones. And so this is one where we'd love to work with you. Either if you're building cool demos, then we can highlight them and we can show off what you've done and show off the cool things that are possible. If you work for a company that's working on AI stuff and are interested in being a launch partner, we'd also love to highlight your work and your company and help cross promote and do things like that too. And so we're very, very, very excited about this. It's been a hard and a long path to get here, but we think it's going to be really something special. If you haven't followed, we have been massively improving our licensing situation. And so we want people to be able to take Max and use it for basically anything. And so you shouldn't feel worried about using Max for cool things. The thing, as a business, we do need to make money at some point here. And so the thing we're carving off is managed cloud deployments. And so if you're in that space and you want to use Max for something, please just reach out. We're very friendly. We're happy to work with you. But if you're developing locally or building something into your enterprise or whatever, you can take Mojo, you can take Max and go use them for lots of different kinds of things. You can build GPU kernels and export them and put them into your own system or whatever. Like, go nuts with that. We're not trying to keep GPUs only in a modular or something like that. And so coming back to the very beginning, imagine a world, imagine if people could innovate in hardware and they don't get stuck because there's no software to use. Imagine if developers didn't have to learn Rust and CUDA and C++ and like all these and Python and all just to be able to build AI applications. Imagine if we can somehow close this gap between research and production, even just a little bit, what that will mean for the world. And imagine if we have more AI that's actually useful in our lives instead of gimmicks and demos that never get to production. So with that, I think that's the end of the talk. If you're interested in working and helping build us all this kind of stuff, we're actually hiring. We have a number of positions on our modular.com careers page. There you go. So that's the lightning round. Do you want to do questions now, Tatiana, or do you want to?
Yeah, if there are any questions to Chris about the talk, let's do this now.
Cool, Gabriel.
Yeah, sure. It's a bit of a feedback and a question at the same time. So beforehand, it was really clear the frontier between Max and between Mojo. Like, for example, Mojo, you can do pretty much anything, but like if you want accelerated AI, then use Max. Like for GPU, it seems that the line is a little bit more blurry. Like for example, let's say that I want to write kernels for PyTorch. Do I need Max, or can I just choose Mojo? Like it does not seem really clear from a sub point of view, and it'd be awesome to clarify it.
Yeah, so the answer is you need max, right? But let me tell you a couple of things about that. So PyTorch is an AI framework, and so it's not. I mean, hopefully that's not surprising. When you're writing a GPU kernel, you don't just need to get code out. You need to be able to write benchmarks. You need to write test cases. You need to be able to showcase demos and things like this. As modular, the problem we have is that we want people to be able to use things a la carte, but we also want to make things easy. And so the challenge we have is just strictly the complexity that we opt into in terms of what we have to manage and what speeds us up or what slows us down. And so we talked about it. We can't support a Mojo only kind of world, because Mojo without a way to submit kernels to a GPU doesn't make sense. You need a runtime. You need the ability to talk to all this kind of stuff. And so what we're doing is we're putting all of our eggs into make an integrated solution that works well kind of in a basket. Now that said, like Max is actually quite lightweight. The current release has some PyTorch stuff in it, which makes it really heavy, and we're fixing that. So when we fix that, it'll be basically the same size as the Mojo package used to be, including Max. I think that'll be done in a month-ish, something. And so I don't think there's a downside of having Max. So what we're trying to do is we're trying to simplify our lives and be able to move faster. So
Thank you.
Is there a reason that you're concerned about having Max?
No, it's just because like when you download them, you have to specifically choose if you download Mojo or if you download Max, and like it's a question that everyone has when they start with
I
Mojo.
agree.
Like, what do I need to download to start working? And so
I agree.
logically, they need to understand like why there is two different things, and
Sure.
if
Well,
they
so-
need them.
So we're actively working on that, and and I'll be straightforward with you. The basically the only reason we have two things is that the Max package includes, I don't exactly know, but it's many hundreds of megabytes of PyTorch stuff, right? And so the difference between a couple hundred megabyte package and then a gigabyte package is a big deal. And so what we're doing is we're saying, let's push PyTorch out of the package, have all the fully native technologies, super awesome. I think I don't exactly know. Jack, do you happen to know how big the final package will be?
No, but Zach's here. He'll probably have a better idea.
That's it. Awesome.
Okay. One
Yeah,
more question.
thanks. It's really clear.
Zach, do you know how big
Yeah.
the final package will be?
Which package? Sorry.
The Max package in about a month.
So the Max package, it's going down at least about 100 megabytes. So the current Max package is around 300-ish, depending on platform. So it's like 250 on x86. It's about 300 on ARM, but it's smaller for some reason on Mac. But it will go down about 100 megabytes for, and that's fully compressed. So uncompressed, it's about a gigabyte. So that should go down uncompressed by, I think, don't quote me on this, about 300 megabytes.
So it's in the small couple. So it's getting small, and so
Yeah.
what we're pushing on is make it so we can get to one thing. We
Yeah.
can get to one thing. It will simplify our lives, and this is also why we're getting rid of auth to make it so people can download. We're going to have pip and conda packages, which we'll talk about in a couple of weeks, to make it super easy to install, so you don't even have to use weird installers, and just make it so you can get full access to this.
Yeah, it's kind of great with the PyTorch unbundling, as we're calling it, where it one of the problems that we have right now is we have PyTorch inside of, if you ever zipped a zip file, you can't sort of reduce duplication in those senses. So this solves that. So it gets things dramatically smaller across the board.
Yep. Sora.
Yes, hi. Can you hear me?
Yep, we can hear you.
Okay. Yeah, but having Max and Mojo, well, they always back this same question. Like, then it's not very clear how much of the GPU support is in the language and how much is supported by the runtime and by the Max framework, right? And also if it affects how much we can expect to see it being open in the future. So I guess many people have the same question.
Well, band, let me expand. So I'll try to answer these as best I can. So we're merging Max and Mojo packages so that we can have one thing. Like this isn't done yet, but we want to get to that, and we need to make it smaller before we can do that. But separate from that, within the Max package, which includes Mojo and this whole technology, it like using a compiler without a runtime doesn't really make sense. And so what we're doing is we're making it so Max is available under the same license as Mojo. Right, we just want you to be able to use all this stuff for lots of different things, and you shouldn't have to worry about is one thing good or one thing bad. There's no difference in terms of license or things like this. Also very modular in terms of dependencies, and so if you care about code footprint and things like that, we've got you covered. And so that's what we're doing. And so I think that the point here is that we're trying to get to a unified, consistent, simple world that just works, right? And the only way to do that is have integration.
So if you allow me to make the question even more straightforward, can we expect the Max part of this Unity to be open source someday?
Oh, okay, I see. So open source. So we're definitely open sourcing big chunks of it. I don't know what the final end state is, and so we'll have to work through that.
Okay, then yes. Thank you for that.
Okay, we have time for one more question. Hunter.
Yes, you mentioned, can everybody hear me?
Yes.
You mentioned that you were introducing a new package manager for Mojo. Is this going to be more of like Cargo, that's sort of package management, a build system, formatting tool, the rest of it, where there's kind of a standard in the Rust community, or is this more going to be like pip, where there's 10,000 tools and nobody knows what to do?
So what we're doing right now is we're getting Mojo, and so the Mojo compiler and tools and the Max stuff to integrate with existing stuff. We want to make it so you can pip install Mojo, which doesn't really impact Mojo packages. Our longer term direction in the immediate term is we want to make it so that Mojo integrates really well with all the Python ecosystem. And so we haven't done this yet, but our dream is that Mojo is the best way to extend Python. And so again, we're scoping right now. One of the things we'd love to do is make it so that you can write some Mojo code and potentially a hybrid Mojo Python package and just make a pip package and not have to do PyBind or like any of this nonsense. Make it super simple and super easy. And so we haven't done that yet, but hopefully that will be coming out this fall. And so that gets us out of having to build a package manager and makes it so we can just integrate really cleanly with the entire Python ecosystem. Somewhere down the road, we can look at going beyond pip and conda and things like this, but right now, integration with Python and leveraging all the things that make Python great is really the right immediate path.
The other quick thing was I just wanted to say thank you. I'm not using Mojo for any of the AI or performance benefits. I'm using it solely just to compile Python to simplify my deployment, and I'd like to say thank you for that.
Yeah, that's awesome. And again, this is where we're very focused on a set of like Chris has access to grind with heterogeneous compute, et cetera. But I'm really glad that what we're doing is useful for lots of other things too. So,
any ETA on classes?
All right, Tatiana, let's pop out of this. We can do general.
Okay, sorry.
Let's pop out about this and let's hear the talk about async, right? And then we will have a little bit more time for Q&A. And Brian, this is all yours. Please tell us about Async Mojo.
All right, if you can hear me and I'll share my screen. Just confirm all that good stuff.
Yes, we can hear you. Please share the screen. Yes, we can now see the screen.
Okay, so I'll begin. So this is basically my talk on what I want Async Mojo to feel like when I'm writing it. I've structured these as 10 quote-unquote
Hold on
simple
one second.
rules.
Can you switch your computer to full screen mode so that it's just the slide, if it works? There is usually a button in some corner which makes the slide take the whole screen. Yes, thank you.
Okay. So first I'll introduce myself. My name is Brian. You can find me on GitHub under the username given, Brian MJ. Right now I'm having some issues with GitHub. So right now don't contact me there. I'm contacting GitHub support for some help with that. You can see me on Discord. If you have any questions about the talk or you want to connect with me on LinkedIn or anything like that, you can connect with me there. Okay, so full disclosure, I'm not a library expert or a low-level programming expert. Right now, I'm just studying computer science. And I'm not prescribing any concurrency model right now. I just want to share my opinion and start a discussion on the topic. So when I wanted to think about how I wanted to share my opinions, I structured these as 10 rules. So because I'm an ordinary programmer, I want these rules to also be followed by ordinary programmers, and what learning materials they have and how they use libraries. And I don't want to be dogmatic about this. You can break them if you need to, but I think they're good guidelines, and they're meant for the majority of application code. So the first rule, no unnecessary waiting. This is kind of the big reason why people adopt concurrency in the first place. You want code to go fast. So the current situation of computer hardware. Right now, single-threaded CPU performance isn't doing so well. How you get performance right now is by adopting concurrency. So asynchrony and parallelism. So everybody wants their applications to be scalable. They want to scale to millions of users, hopefully. And they want their apps to be responsive so that users get a good experience. So for both of these things, async actually helps a lot. So IO-intensive applications, they require async because you're balancing connections with multiple users at the same time. So one myth in the Python community is that async is for IO. If you're doing something computer intensive, you don't need async. But when you go into Mojo land, where you can actually take advantage of all your hardware, you realize that async isn't just for IO. It's also for compute-bound tasks, because you can take advantage of task parallelism, which is basically like you have multiple tasks and they happen to be independent of each other, so you just run them in parallel. And also accelerators like GPUs, TPUs, etc. So learning materials. When we teach someone to wait for some time after running a task, the first thing we teach them is use time.sleep from the Python standard library. So we don't necessarily teach them right away that this is actually a really bad idea. If you're waiting for something to happen, you shouldn't block the entire thread you're executing on. You should make it so that you're waiting on this thread and spinning up a task to run on another thread. So in short, this rule is basically about defaulting to asynchrony and parallelism. You shouldn't make these two things seem like scary expert-only stuff meant for wizards. They should be adopted by the general program. So if you're curious about this, I've attached some references at the end of these slides. I'll upload them to the meeting doc. You can see them later if you want. So next rule, no data races. I think this is the only one that people will agree that should be enforced, like no exceptions. So if you see how beginner programmers ask about concurrency, and usually if you see in programming languages like, let's say, Java and Python, people will talk about how these you get these weird bugs that are very hard to debug. So you shouldn't bother with concurrency unless you absolutely need it. I don't really want that to be the case. Like I said, I want concurrency parallelism to be the default. So with that, we need to make the DX as useful as possible. And if we look at programming language safety, this is a big topic recently. The most of the talk is about memory safety, but thread safety is also one part of this. And if you look at bugs like data races, they are the worst kind of bugs, because the worst kind of bug is the one that you can't reliably reproduce. So one way to deal with data races, you just ban mutation. Anytime you want to change a value, you make a copy. So this is the approach that purely functional programming takes, but unfortunately, it's not very good for performance, because you're making copies all the time. You're adding a lot of overhead to your program. So a better way to do this is you keep mutation, but you make sure that anytime you're writing to data, that the writer has exclusive access to it. Okay, and there are plenty of languages that have tried to deal with this. I'm just listing 4 of them here. If you want to know more about this topic, you can look at the references again. Okay. Next rule, no unstructured concurrency. So nowadays we don't program with gotos. We have like very weak gotos in that form of like break and continue, but actual powerful gotos where you can jump to another function from out of nowhere, we don't use those anymore. So let's do that for concurrent programming as well. If you look at current programming languages, how do they not enable structured concurrency? So what I call the fire and forget style, this is how they usually fall short. So one of the rules of structured programming is that every piece of code you have should have one entry and one exit point. If you program in a fire and forget style, where you start a task and then later you have this handle that you immediately start a task, your code now has 2 exit points. So here's my one more quote unquote simple rule to prevent this. Anytime you start work in a code block, let's say a function, you complete that work in the same code block and then return. Again, this is for application programs. I don't know how this would apply to library stuff and low-level stuff. If you want to know more about structured concurrency, some more references are here. So does this affect performance? If you're starting a task in a code block and completing in the same code block, does this affect performance? I don't think it does. Because what you can do is, if you have something that you're running in the background, let's say, you can just run that in parallel. And one more thing is, can you write all concurrent programs this way? So I can't give you a definitive answer. I can just point you to someone who has written an informal proof. It's given in the reference here, the link to it. So next rule, no raw threads. And by raw threads, I mean operating system threads. You're not directly using them. So OS threads, they're not known for being very performant. If you look at this chart, it basically talks about how many CPU cycles different operations take. And if you see, the most expensive of these two are thread context switches. By the way, this is a logarithmic scale. So every time you're going from one vertical line to the next, it's 10 times the increase in the number of cycles it takes. So over here, you're talking about 10,000 times more than the task over here. Okay, so we know that OS thread context switches are pretty expensive. And if you're writing a concurrent application, you need to be switching between tasks very quickly. So you need context switching to be lightweight. So a better alternative to this is what we call green threads or userland threads, or there are many names for that. I'm just going to call them tasks. So these tasks, what you can do is you can just run them on a thread pool. So you have tasks and you have threads. The threads are managed by a thread pool. You're not directly using them. So because you're not starting and stopping over threads and context switching between them directly, you can just rely on the export low-level programs to take care of the low-level details, and you can program it with tasks. You can put as many tasks as you want on your thread pool. You don't have to worry about thread over subscription and things like that. So the thread pool, usually what people do is they keep it as one thread per core. If you keep one thread per core, you're minimizing the amount of context switches you do between OS threads executing on the same core. Okay, so usually now operating systems have their own thread pools. Windows has the Win32 thread pool, Apple has Grand Central Dispatch. So if you use these, you're avoiding the number of thread pools that you're keeping on your hardware. So this is another way to avoid oversubscription. So if you want to know more about oversubscription, yeah, I've kept another reference here if you want to know. So how do you run these tasks on your threads?
Yeah,
There's
I'd like
another
to interrupt here, Brian. Thank you. We are running out of time.
Yeah.
Do you have any slides which are actually a little bit more concrete? These are fantastic basic principles, and I think majority of people would agree with them. But do you have anything which actually more closer relates to Async Mojo?
Relates to Async Mojo as in like a library proposal, maybe. Is that what you're asking?
Yeah, because we are basically almost out of time for this talk, and I just wonder if you wanted to talk about how these general principles relate to your experience with Mojo, or
Yeah, so most of the time I'm just using Python, and Python, as you know, executes only on one thread, and the only async I use is the event loop async IO. So all this task parallelism, I don't use them much, and I've written a very little code in systems programming languages, so I have some experience with them. So that's why I said I wanted this to be about starting a discussion, not necessarily prescribing something.
okay. Well, thank you so much. I think, yes, in the future, just all the presenters, I would appreciate it if people focus on topics which are directly related to Mojo, since this is like Mojo community meeting. But thank you. We have a little bit time left for questions right now. So, oh my God. Yeah. So let me share my screen. Okay. Okay. So there was one question about date, time, location for MatCon, which Chris already answered. And right, and Chris, do you want to repeat this?
Yeah, so we don't have it nailed down. We're probably not going to do the same kind of event that we did last year this year. We will do it again, but it's not going to be this fall probably. And so we're talking about doing a smaller event that'll be more developer focused, but we don't actually know yet. So we'll let you know as soon as we know. We're excited about it. We want to do something cool. We're also talking about doing hackathons. And so that's an idea that we're looking to explore that we don't have a really clear plan on yet, but we'd like to try some of those kinds of things as well. So yeah, so we're figuring this out.
Okay, thank you. Martin, how far away are we from being able to compile for a microcontroller like an ESP32 and fit the binary in 1 to 4 megabytes? I know it's not a priority, just curious on what the obstacles are. Anybody on Modular team wants to take this?
I don't see anybody that be the obvious person to respond to this, so I guess I can cap fill. Well, so there's two questions when you're talking about microcontrollers. There's RV32I, which is that a RISC-V? I'm not exactly sure, but so there's a code generator, but then there's the architecture piece, and so we need to be able to provide different code generators and things like that, which we don't do right now. But I know people put Mojo on Raspberry Pis and things like that seem to work. In terms of being able to get a small binary, that should be fine. I mean, you look at GPU, a GPU is basically an embedded device. And so a lot of the architecture of Mojo is really about being able to scale down and have zero dependency work. And so it should be fine. There's sometimes some minor nonsense that has to do with like start logic. And if you're bare metal, you have initialization stuff, whatever. But generally it shouldn't be that big of a deal.
Okay, thank you. Okay, several questions from Gabriel. The first one, okay, what's the status of standard library meetings? Are there any in use, and how can the community help with that? Do we
Joel,
have...
do you want to take this?
Yeah, sure. I'm happy to jump in. Right now, there's not any active plans for immediately starting the standard library contributor meetings that was originally talked about, I don't know, a little bit ago at a previous meeting here. But it's something that we definitely can plan for in the future. We just opened some job posts the other day. And so I think as we ramp up the team and allow for some more bandwidth, that's something that we can definitely explore. Right now, we're still trying to figure out some of the Q3 plans. There's been a little bit of change in immediate short-term plans. And so we're trying to figure out how we can get the standard library team and the community involved. And I think that would be a great opportunity to connect all the dots there.
Okay. Thank you. Lucas, are there any near-term plans for C dynamic static library linking and the modified external call syntax? Or alternatively, a workflow using static lifetimes with dilibs and alias as a way to avoid every struct calling into C functions growing a lifetime. This will be super important to get things like OpenSSL bindings or interface better with specific OS libraries that don't make sense in the stdlib. And we have issues about that.
I think Jeff would be the natural person to talk about this. He's probably thought about it the most. So linking, so two things. One is linking and one is external call syntax. So there's active work going on right now to improve the compilation model. And so this is a big part about making it so that Mojo can integrate well with Python and C++ and things like this. I think that will directly help, and that's actively happening in the next month or two. The second part is the refined external call syntax. So there's a clear path to that. That seems obvious to me. It's not staffed right now. The way to make that happen is when you import an external module, just use Clang to parse the header files and then remap C APIs directly into Mojo. That's what Swift does, for example, and it works really well. It's a heck of a lot of work, particularly making it good. And so I don't think it's going to happen in the next couple of months, but it's something we'll do at some point for sure. So I think that the linking part is actually the bigger priority because that becomes more of a blocker. And so that's why we're prioritizing that first.
Okay. Next one again from Gabriel. What tools are we using to profile in Mojo?
I'd really love for somebody else to take this question.
Yeah.
Yeah, so there's a variety of tools that people are using internally. It's kind of just ad hoc at the moment. But yeah, like after you posted that Discord comment, I've been looking for people to write a blog about how they use profiling tools, and then we can share that with the community as well. So we'll work on that for the future.
Thanks. Great.
Okay. Okay, Python has a garbage collector to handle circular references. Since Mojo wants to support most of Python syntax, is this possible to handle those in Mojo without garbage collection? Or will users need to use weak references or something similar?
So, I mean, you're asking what does Mojo grow into? I think that we're evolving and iterating as we go, and so we'll figure it out as we go. But I'll say that it would be really awesome to not have to do the Python style circular GC cycle collector thing. I know it can be done without it. This is like Swift, for example, is an existence proof. Rust, for example, is an existence proof. And so I'd say the burden would have to be extremely high to add a garbage collector to that. And so we'll do pretty much everything we can do to avoid that. Now, that doesn't mean, so if you're importing an external Python package, and so you're using CPython to run an existing Python package, then of course that will use the existing Python tracing collector. And so we'll be compatible through that way. But yeah, I think that we'll have weak pointers and other things like that when we need to do that. Hunter, you're asking very politely about classes. We're not planning on starting that in the next few months. Maybe theoretically it could be started this year by the end of the year, but I think feels like it's probably more likely early next year. But it really depends. It's hard for us to really project beyond 3 months because the team is growing and we have a lot of other things going on.
Okay.
And yes, we will do classes. It's very important. So
Okay. So the struct object currently has a variant inside to handle a fixed amount of structs. How will that evolve to store any struct in a program?
Yeah, so we're actively debating object and Python object and the integration between these two. The feature we actually need to do this right is called existentials. It's where you have, Russ has a name for this. That's where you have basically dynamic traits. And so you say, I have a thing and I don't know what it conforms to and it gets boxed. And so basically we have stopgaps until we implement existentials. And so object and Python object are both kind of really unfortunate for different reasons. And so we'd like to fix this. In the meantime, a thing I would love to see, and Joe L, please don't strangle me. I don't know if I'm going too far on a limb, but is pulling object and Python object together and having one thing, I think would be simpler. It would mean that if you define a def and it's not, the arguments are not typed, it would mean that you would get something that works with Python very naturally. And I think that would be a huge step forward. Object, Gabriel, you're being maybe polite here. Also, object is really half-baked, and it's one of the oldest types that we implemented, and would love help with fixing it and cleaning it up and doing the stuff. Fundamentally, when you're talking about something like an existential, or you're talking about an on-the-stack box, you have to decide on a fixed size amount. And so the traditional way that you handle that is you have some small fixed amount of space that can be in line, for example, 2-3 words, something like that. And then if you have an object that's bigger than that, then you box it and put it on the heap. And so I assume that we'll have, when you get existentials, you need something like that because you can box unknown arbitrary size things. And so we could prototype that and implement that now, even without the language feature. And it'd be a little bit verbose and boilerplatey, but I think it would be the natural way to solve this. So you get basically an inline storage, which can be an out-of-line pointer, and then you get a vtable.
Thank you, Chris. Last written question. Will Mojo support higher kinded types or C++ template parameters?
I think it already does, sort of. So, I mean, I think that it depends on exactly what you're meaning. I would really channel this. My abstract request here is don't channel it into higher kind of types, which is a very loaded term that means many different things in many different languages, and it's like a general PL theory question. And instead, channel it into a concrete, can you do X? Can I express Y? Can we do Z? And I think that it's much easier to answer. Obviously, we're not going to have template parameters because we're not C++. We don't have templates. But if you're trying to say, I'm trying to solve this problem with Mojo, how do I do it? I think that would be an easier kind of question to answer.
Okay. We answered all the questions in the document. Do people here have any more questions? This is not meant to be just
Actually, I have to jump, but it's great to see you all. Take care.
Okay, well, we'll try to answer. Sora.
Yes. I really want to know when or what kind of pattern matching or EDAM sum type support will we have?
Can you repeat it? What kind of?
I want to know if we are going to have pattern matching and with that sum type or ENUM.
Okay, pattern matching.
The short answer is we've talked about this sort of thing in the past internally. It's definitely something we want in the language, but it's not on the short-term immediate roadmap from the language compiler side. So yes, but not now.
Thank you, but sad.
It's a small team with internal priorities right now. I hear you.
Okay. Yeah, sorry, things take time. Good things always take time. Okay, any more questions? Okay, thank you, everybody. See you in 2 weeks.